Welcome back to Advent of Code 2019, day 18. Hello, DJ. So today is a non-int code problem. It seems every odd-numbered day is int code, which was yesterday. Today, this one looks like some sort of searching, pathfinding, shortest path algorithm. It looks like a traveling salesman problem, which is NP hard, but okay, so man, I was so excited for ink code. Yesterday's I solved by hand. I solved part 2 by hand, which is strange. Well, at least most of it by hand. Running the int code problem obviously needed to be done programmatically, but yeah, it felt like it would be quicker to solve by hand than to actually write a program to solve it in this particular instance. Okay. 18. Many worlds interpretation. Oh, I forgot to put the kettle on, and if I put the kettle on now, it's going to be really noisy. Unless I put kettle somewhere else. Let's read a bit of this first. As you approach Neptune... Okay, so we've arrived at Neptune. So, from what I understand, these planets are... Well, one of them is not a planet. So we've got Mercury, Venus, Earth, Mars. And then this one is the Ceres monitoring station, apparently, which seems to also be orbiting the sun. But then everything else after that, it's Mars, Jupiter, Saturn, Uranus, Neptune. So we're on to Neptune now. And then I guess Pluto is off in the distance there. If we count it as a planet, I can't keep track of whether it is or isn't a planet at this point. All right. I think it's now not a planet. As you approach Neptune, a planetary security system detects you and activates a giant tractor beam on Triton. You have no choice but to land. A scan of the local area reveals only one interesting feature, a massive underground vault. You generate a map of the tunnels, your puzzle input. The tunnels are too narrow to move diagonally. Okay. I can deal with that. Only one entrance, marked ampersand, is present among the open passages, marked dot, and stone walls. Yeah, sure. But you also detect an assortment of keys, shown as lowercase letters, and doors, shown as uppercase letters. Oh my god, is it one big keys and doors puzzle? Is this like some sort of Legend of Zelda type algorithm? So we enter in the center here. So I'm guessing we have to find the corresponding small letters for the large letters. Okay. Interesting. It's some sort of breadth first search, except your nodes are not individual cells in the map, but your nodes are actually keys and doors. So you're kind of, instead of deciding whether to go up, left, down, or right, you're deciding which key do I go for next, or which door do I go for next. So all your keys are neighbors, or at least the accessible ones are, and all your doors for which you have a key are also neighbors. So then it's that sort of breadth first search, a different kind of breadth first search. And there's an inner breadth first search you would need to do to find the shortest distance to the doors and keys as well. I'm getting ahead of myself though. That might not be what we're trying to do. Keys, yeah. Okay. You aren't sure which key you need to disable the tractor beams, so you'll need to collect all of them. That makes it easier. Then I know I need to collect all of them. I don't need to decide which ones to discard or whatever. Starting from the entrance, you can only access a large door, A, and a key. So the goal... Oh, the goal is to collect every key. Interesting. How many steps is the shortest path that collects all of the keys? Interesting problem. But I think what I said earlier is the right approach. Just a breadth first search, like a double layered breadth first search. Interesting. Is it? It's not a tree, is it? It's... Are there loops? Well, there are loops. Well, there's at least one loop here. Hello, Flynn. Yeah, back on the AOC. It looks mostly like it's a tree, i.e. there's no cycles, which will make it way, way easier. It might not be. I mean, not that it matters. We write the algorithm similarly. So at every kind of phase, we want to make a beeline straight for either a key or a door that we hold the key for. Wait, no. We don't even want to head for a door. Why are we heading for a door? Every step, we only choose a key which is accessible. So any key that's locked behind a door that we don't have a key for, that's an inaccessible key. So we do a flood fill, basically, to work out which keys are accessible, taking into account which keys we're holding. And then the outer breadth first search will be choosing each of those as possible neighbors to go to. So it's not quite like a traveling salesman. Well, it is sort of, but... It's kind of... It is a traveling salesman problem, but it's in a sort of tree, or a very tree-ish map, which would mean it would no longer be MP complete. Kind of. And this here is sort of a cycle, but you can this 3x3 space in the middle, you can compress it down to be a single node in theory. So it's technically a cycle, but not really. You can contract it. I don't think there are cycles here. It's hard to tell. But it looks like it's a very low cycle count anyway, so that would imply that it's a tree, in which case it would be polynomial. Yeah, and so you would just use pathfinding as normal. Interesting. Okay. So there are how many keys? It looks like there's one for every letter of the alphabet, so 26. So there's 20. Breadth is 26. We're trying to find the shortest path. But the state space is the tricky one, because you could have 2 to the power of 26 different assortments of keys in your inventory. It's actually strictly harder than Traveling Salesman on a Tree, because they put doors in the way. So there's like a wide range of possible assortments of keys you're carrying. So the state space is where you're standing combined with what keys you're carrying. Now, even though there are so many possibilities there, like so it would basically be 26 times 2 to the power of 26. So it's that many possible states. So it's like 2 trillion. But I don't think we'll realize all of those states anyway, so... I'm guessing the doors are sort of forcing a topological order here, so that most of those states are not possible. Like, you can't have the late keys without having the earlier keys. So I think it will just work. If we just run breadth first search, it might just work. Well, we'll run it. I mean, if it doesn't, then what? Maybe we have to look to some sort of topological ordering, like work out which keys must be accessed before other keys. But I don't think we would need to do that. This is a part 1, so it shouldn't actually be that difficult. We'll see. I mean, if we weren't doing it, the brute force C type approach would be try all possible orders of keys, of which there are 26 factorial. Which is too many, of course. But yeah, all right. Breadth first search then. It looks like they've sort of placed doors in places that would mean at any stage you can only get like 2 or 3 keys, maybe, or something else, something like that. All right. Let me just put the kettle on. So have you been doing? I can't remember what you said, Flynn, before. You've been doing 2019 or a different year? Also, I have a leaderboard. I haven't checked it in a while. I did several... Hang on. I'm using a new chat tool and I can't scroll down in it for some reason. I did several rewrites of this. From first opus. Ah, okay, you are on the leaderboard. Oh yeah, I did notice that these two popped up recently. So, yeah. Cool. Alright. Let me put the kettle on, and I'm also trying to... sort out the chat window there. I think that's fine. Okay. I'll leave the description up. I have to go find a socket somewhere so that the kettle won't be loud on stream. All right, so still pretty loud, but all right. 18. The input. I've had so much practice with these 2D grids, so I'm starting to get the hang of them. Alright, so we put the raw string in each row of the grid. Should we wrap this up as a class? Because we'll want like a shortest path method or something. Should we do this in the constructor? That's probably not advisable in Python, but I don't see any reason why not. This is wrong. It should be... Okay, we'll sort that out. Self.grid equals that. For line in f.relines. Grid.append line.strip self.grid. Right. So want to record some locations, I guess. Just like a map of all We don't care about where the doors are. The doors just happen to be there when we're traversing the graph. We do care about where the keys are, because those are our nodes that we're actually heading to. The doors are mostly irrelevant unless we happen to walk into them. Right, so during this process, probably want to let's copy some vector class that we used before. So on the even numbers probably are when did I use a vector? Well, that was like a 4D vector, 3D vector. No, we didn't do it there. I can't remember. Pos. It was pos. Oh no, that was just a raw tuple. I'm sure there was some place where we had vector defined with addition and all that. We'll just go through each of them one by one. No. Oh, it was asteroids one, maybe further back. Should I just write it from scratch? Yeah, but this is the asteroids one, but this is not what I was thinking of. Okay, we'll just write it from scratch. Okay, so we want a call it a pause. Let's make it a data class. This is a really cool new thing in Python. I say new, but it's been around for ages now. But so no, we want rows and columns. Yeah, rows and columns. So row. No, I's and J's. That kind of means rows and columns, but I's and J's. All right. Okay. Data classes. No, we just data class, right? Can we just... Oh yeah. From data. Okay, just leave it like that for now. So as we're going through this grid, we want to find all the relevant things. So keys. Let's call it. Just make a hash map. So for each small letter, so we're saying or, so it'll be for the J, so it'll be, let's say for I, line in enumerate. Got read lines. So that'll get the row. For j r in enumerate line dot strip. If dot l dot is other string methods to see if something's a lowercase. Or you could say is if dot lower equals. Let's just check if Python check if character is lowercase. Is alpha. Oh, there's an is lower. Okay. Is lower. But you also need to check is alpha because it will probably return true on other symbols. So we want self.keys. So it's going to be pos ij. So the character is mapped to pos. I was just going to ask about that. I checked both. Yeah, I think you do need to check both because it's designed for using with like sentences and natural language. So all the commas and full stops and everything, it's going to just return true vacuously for them. Let me grab my coffee as well. Alright, so we've stored the keys. Elif equals ampersand. We will probably want just keep track of what we're actually storing here. Self dot start. Anything else? That should be it. Doors we don't worry about. Okay. Okay. So we probably want some methods here, like for example, is walkable. Define is walkable, or define get pos turn self.grid pos 0 pos 1 define is walkable is not equal to hash. Because there's walls around the outside, you can never actually end up being out of bounds. So we don't even really need to do out of bounds checks. It would be good practice to do it anyway, but... nah, because our neighbor method is going to be walkable neighbors, so we don't really need to do that. Get neighbors then. Define get neighbors of a given pos. For delta in, so it'll be zero, pos -1, 0, pos 0, -1, pos 0, 1. Well, we don't have an addition. We should really do that now. Okay. Subtraction? I don't think we even use subtraction. Hash and equality we get for free because of data class. Anything else? Distance? No, we don't even need distance. We're not using A-star search or anything like that. I think that's fine. Neighbor equals pos plus delta. If is walkable or neighbor, self-dot is walkable. Yield neighbor. So that yields all the walkable neighbors. Okay, so far so good. Nice and clean. What else? I'm gonna have to hello original bugle. What is yield? Yield lets you treat your function as a generator in Python. So if I were to, I don't really want to return a final value and finish the algorithm. Instead, I just want to sort of return things as I compute them. So if I were to now do this for neighbor in get neighbors, right? Well, get neighbors of a pos or whatever. It would start running get neighbors, but the moment it hits yield, it will return that one value, and that will come out of the generator, and then it will stop. It will pause computation until you request the next one. So then in this inner loop, we'll just do whatever we want with that neighbor. And then the moment we want a new one, we'll then carry on computation. So it's like, it's just lazy evaluation sort of. It's only doing as much work as it needs to get to the next neighbor and so on. So we'll fetch each neighbor, I mean, the end result is the same in this particular case because it's not exactly a very high computation method, but it's just nice and efficient because now we don't need to make a list, because normally you would do this. You would say neighbors equals list. You would say neighbors.append neighbor, and then afterwards at the end you would have return neighbors, and then this down here would still work, right? Because you've got a list instead of a generator. But if you wrap everything up as generators, it's just kind of nice and efficient, and then you have some optimizations and all this stuff. And it's fewer lines of code as well, because now I don't need to explicitly create this thing. It's just yielding whatever it's computed at the time that it's computed. But you can do nice things with this. You can make infinite generators, and you never worry about getting into an infinite loop, because you could just say like you could just have an iterator that increases from 1, 2, 3, 4 and yield each of those, and basically you've created an infinite generator which gets a new ID number. That's a good example, actually, creating ID numbers, because you want to always get the next available ID number that no one's using yet, so you just increment a counter. And that's an infinite method, but you'll never have infinite computation because it's like it only computes the next ID number when you need it. So you can do some cool things with generators. It's one of the very Pythonic things which thought I understood yield soon after I first encountered it, but still trying to wrap my head around generators, especially the way the Encode implementation works with it. Yeah, the Encode, the way that I've done Encode, there's still a couple of things that I don't fully understand why they work, but they do work. But yeah, I mean, it's a quite complex thing, and it's similar to like stuff that you do when you study functional languages like Haskell and stuff, treating everything as a function and but yeah, I mean, those basic examples are you can do a lot with those examples I've just described. And like if I actually want to finish explicitly, I can say return, but you don't need that. But you may want to return under certain conditions, so it will automatically like stop once there's no more neighbors in this particular example. But yeah, I try to wrap everything up as these generators because it's a bit cleaner. You just have to remember that what you get neighbors will return a generator. So it's not like you can do length off get neighbors or anything like that. You do need to fetch the neighbors, but you can do like list, cast it to a list if you wanted it as a list. And if you wanted to sort that list, then you could then sort that list and so on. I mean, you could do this. Sorted get neighbors. Oops. Now, I think in order to do that, it would actually have to compute all the neighbors behind the scenes, and then it will return them in a sorted order, I guess. It also avoids having lots of kind of like variables, like lists floating around, which then have to be deconstructed later. Initially explicitly saved the state when it was supposed to get input, but then realized that the yield just pauses without doing that because of the generator aspect. Yeah. Yeah, I think the Python's yield made the whole Encode implementation very interesting. It must have been a lot harder to do it in the Encode stuff in C++, managing this concurrency type thing that we're trying to do with inputs and outputs. Thanks for the follow, Original Boogle. Are you doing advent of code yourself? Or have you done any in the past? Alright, so I think those are all the helper methods we want. From Q, we'll need a Q. The breadth first search. So we've got the start location and the doors. Oh, we could have a helper method to deal with doors. Or just check that in the BFS. We can just say, define needs key. A given pause, well, it is the Boolean expression saying whether we need a key to access this particular spot. So, and it returns let's say required key. So it's telling us what key is required to access this spot, or none if no key is needed. So let's say if so we're saying if it's upper, if get neighbors what is the goal about your program? If you can explain easy, please, because I don't speak very good English. All right, so let me also post the link for the site. I don't know if you've seen it. So that link is the problem I'm trying to solve. It's a puzzle, basically. And the general gist of it, the simple explanation is that we have a map, we have small letters, which are keys, and we have big letters, which are doors. So a small letter C, if we pick up that key, it's like in a video game. If we pick up that key, we're now allowed to open the big door, C. And if we pick up E, we're allowed to open big E. So we start at the ampersand, which is the middle here, and we have to collect every key, but we can't get through doors unless we have the corresponding key. So you have to figure out the shortest path to open, collecting all the keys. So it's like you might go to B first, then unlock, pick up G, unlock B, pick up N. I don't know. Something like that. You have to work out the shortest path to collect all the keys. Just say equals that. So if car dot is alpha and it's upper, oh, why get neighbors? No, get pause. There we go. So if it's an upper, then we basically return r dot lower. Turn none. Okay, so that's just telling us the required key, if any, to access this spot. I think we've got everything now. I love data class. Okay, so... So we're saying a state is the combination of position I'm standing in and a hash set of the keys that I'm carrying, so that its order doesn't matter. And because this is a data class, it already knows how to hash positions. Wait, hash... No. Well, a hash set itself would need to be... Thanks for introducing me to data class. I was having trouble learning the base Python class. Data class simplifies a bunch of stuff. Yeah, it does. And it's been around for a while, but I only started using it, I think, last year. I knew about it in the past, but I just kind of kept putting it off. But yeah, it's just... I mean, when I worked at a company, so many times, it's just the same thing over and over again. You write a class, and then you have to spend ages listing all the variables and the... and then in the constructor having to set this to this, this to this, this to this. It just takes away all that, plus gives you the obvious equality check, the hash check, which you can override if you have a more complex logic. But yeah, it's just, there's so many easy classes you make where you don't, where you know it's the obvious approach just works, like testing the equality of the 3 parameters or whatever for a 3 integer vector. But yeah, it's good. I'll go to eat my breakfast, but it is a good stream soon, thanks. Alright, thank you, Original Bugle. Over the next few days I'll try to do more of these Advent of Code problems, because I'm trying to get this done. But yeah, in the case of this data class, we can also make it frozen, which in this case makes sense. So let's do that. That means it's like, it is a immutable vector. So you're not allowed to change IOJ. That means it's hashable now. I think if I didn't do this, it wouldn't be hashable. So I actually do have to do that. Gotta just marathon the last couple days. I don't know how hard they'll be. The last day is usually not too hard because it's Christmas Day. I'm sure that Eric is well aware that he is depriving us of our families, because we will spend the whole day solving Advent of Code if we need to. Not that I ever really spend Christmas with my family. I'm usually halfway around the world from them, but yeah. We'll see how hard it gets for this year. Will it be an encode problem? Hang on, so it's what? It's odd numbers. So it could be an encode. Yeah, it probably will be. Alright, so let me... Alright, let's run this because... Yep, no crashing. Okay. I'm really enjoying the encode stuff. Yeah, this was definitely a very unique year. I don't think he's done this again. Like, I haven't seen 2020, but I can imagine a lot of people didn't like it. It's a very polarizing thing. Some people don't like the fact that if they get stuck on the initial encode problems, then they wouldn't be able to solve any of the remaining ones. I get that. That would be quite demotivating if someone's, you know, a beginner and they... Programming the encode is not exactly easy, and I can see a lot of people getting stuck on that, and then that kind of locks them out from half the problems in the whole month. Especially that concurrency thing, like dealing with the inputs and outputs. Like, that's not beginner level stuff for coding. That's pretty advanced. So yeah, I can see it being polarizing, and that's probably why he's just not done it again. Nevertheless, it was an interesting thing to have for this particular year. More funding than the assembly stuff. Yeah, I mean, yeah, exactly. Once you've got the assembly stuff out of the way, which, again, is kind of complicated, but then it's nice that you've actually got this little computer, which is actually interactable. Like, you're actually giving it inputs, it's giving you outputs, it's literally running a robot pathfinding algorithm behind the scenes and telling you what the map looks like. It was literally running a game of Breakout with the ball bouncing up and down and moving the paddle and stuff. This is... I've never seen anything, any coding challenge like this. So it was really quite clever. And you would never be able to do a challenge like that if you didn't continuously build it up over several days. I'm amazed at what they've coded in that. Yeah, exactly. He spent a long time putting that together, I'm guessing. And you could probably... Python has some libraries where you could make an animation, so you could actually see the ball and the paddle moving in place, rather than just printing out every individual map. You could actually just have the game, you know, running. Maybe I should look into that for next time, because there are several problems which you probably want to run an animation for. Seeing things move about. In fact, that's a great visualization tool. I should actually prepare that for next year's thing. But yeah, cool challenge. As I understand it, Eric is kind of into that stuff, because before Advent of Code, he made some kind of challenges, but they were a bit more on the assembly type side of things. And back then it wasn't majorly popular, so it was just a few of his colleagues and stuff that he was sharing it with. I can't remember what it was called. It's still on GitHub, but it's very difficult to get it working again, because there's no longer a server for it, so you have to run your own server to make it work. But it is some sort of coding challenge which involves a similar thing, creating a computer and running it and doing stuff. I think it's was it the Cinecore challenge? He actually, because Eric worked for, I think, the company called Cinecore, so he actually made it as a tool for, I don't know, maybe interviewing new applicants to actually join the company. So he actually, maybe that was what it was for. Alright, let's actually do this BFS then. So given a start location, which we'll get from the grid, so the initial... Right, let's make a helper method here. Define get state. So given a position and a hash set of keys, because you can't hash a set of keys. If you try to hash a set of keys, you'll just take the memory location of that set, which won't work. So we need to actually take out the keys, put them into a sorted string, and hash that string, or a sorted tuple. Let's go with string. So key string equals, so we're going to take, so we're going to join up all the keys, but we want sorted. I think that'll work. So sorted is another generator. It's going to take the keys in sorted order, and you can just apply this to join them up as one string. So if you do that, then you should just be able to do this. Return the tuple, pos key string. I mean, we could just simplify this. So if we do that, then we should be able to say, initial state equals get state start just an empty set because we hold no keys. So of course we need a queue. Put the initial state in the queue. So we're gonna have to make two passes of this. Well, there's an inner breadth first search we need to do, because we need to actually do a flood fill to see where we can get to in the first place, sort of. Would this be too expensive though? Like if we did an initial all paths, shortest path algorithm, that will get us the distance between every pair of points, but it doesn't take doors into account. And if there are cycles, it's not taking into account that although it would require a door to get from A to B, a key to get from A to B, there may be another path that goes around which doesn't need that, and that is not stored in that knowledge. But then the map kind of looks like a tree, in which case, is the set hashable, or does it need to be a tuple? Technically it is hashable, but the result is not what you want it to be. It's just going to take the memory location where the set is stored, I think. Actually, no. I think it will just complain. I think it will just error. So, yeah, I think it will just error. It will say this is immutable. This is not immutable, so you can't hash it. It needs to be a tuple, yeah, or string, or any immutable thing. had a terrible time turning lists into sets, tuples, whatever, to make that part work. Really? What was the issue you were having? Because, I mean, in the general case, it should just be... sort the list, and then put tuple in front of it, but... still learning what is hashable. Yeah, I mean, that's a pretty complex topic, and the most important thing is that it's unique and that order doesn't matter. So if I have keys A and B, and in another instance I had keys B and A, you want those two to be the same. So yeah, if you sort the list, it will always be AB, and then it actually can see that then AB and BA will map to the same bucket. So sorting is one way to get around it, but there's other ways. So I'm trying to think now whether I should be doing... Is this actually a tree? I think this actually makes a difference, whether it's a tree or not. I mean, apart from this center... How do you test if something is a tree? You run... Well, you run BFS, don't you? That's... BFS is a cycle finding... Oh, it's not a tree. I can see. There is a loop. Yeah, it's... Hang on. Or maybe my eyes deceive me, I don't know. Actually, it's really hard to tell. Yeah, so if I ran BFS, I could probably tell whether it's a tree. We just have to ignore this center, because clearly that's a cycle. But we don't care about that cycle, because it's like... not a big deal, but... in other places, it would be a big deal. Because my worry is, if I keep doing a flood fill between every step, that's gonna be a lot of work. I could try doing it, and if it doesn't work, then we just do some sort of smart tree approach. Like, so I'm standing here, I do a flood fill to see where I can reach. Now that takes kind of like linear time. Well, quadratic time. Linear time in terms of how much stuff is in the map, of which there is like almost 100 by 100 almost, so it's like 10,000. So that's a 10,000 step operation to find all the keys I can access. Then I choose which neighbor to go to. So the outer BFS is linear in terms of the number of keys, I guess. Well, yeah. Well, not quite, because states, a node is keys plus this hash set. So it's basically 10,000 times some indeterminate number of possible states, which could be big. Alright. We'll just try the slow approach. let's say we need a helper method here. Define get reachable keys from a given starting position and a set of keys we're holding. Right, so that will mean we can access doors and stuff like this. So this is going to run BFS and take however long it takes. So it's basically this again, but the state now is just position. We don't care about state key. Number of keys we're holding is not going to change because we just move to the one key and then stop there. So it's sort of like it's just we want a distance table. But once we do this, this is no longer BFS. This is Dijkstra. Because it's not unit distance to each key, different distances to each key. So that means we can't use Q. We need to also import priority queue and use that. Right, well, we'll need to figure this out later. Let's try and do the get reachable keys thing. Alright. While not queue.empty. Get the next item from the queue. Alright, so the next item on the queue is a neighbor that we found previously and added to the queue. If Alright, so if this is a key, then we're gonna let's rename this to held keys. And we want to say just make map called keys, because this is going to actually tell us how far each key is. If let's just make another method. Is key. Define is key. Something like this. If self dot is key, keys it'll be self dot, yeah, just get the character equals dist, the shortest distance, and then we don't take any neighbors from this, because the point is we don't ever want to go further than that key, because in the outer Dijkstra I've changed from using Q to DQ, double ender Q in these puzzles. DQ is easier to use in some ways, just make sure which end you're getting from. Main advantage of Q seems to be locking for threading. Yeah, I was thinking about that, because I never really touched DQ much, but clearly, so Q is a wrapper around DQ, isn't it? There's no, and DQ actually offers a couple more methods that Q doesn't have, I think. I could, you can say while Q. Yeah, let's try doing that. I mean, unless I need something specific from Q, there's what is it called? Is it just... Oh, it's not. It's not. It... Ah, it's collections. Okay, we'll try using DQ, yeah. I actually probably should use it most of the times, because we don't... never doing any threading or anything like this. Ah, so you treat it, it looks like a list then. Yeah, that makes sense. Append and pop left. So pop will be like the stack and pop left will be the... Okay, that's cool. So if it's a key, we now just continue on to the next item from the queue, because we only want the immediate keys and nothing beyond them. So, if it's a door, if self.required key of current not in held keys. Continue. We can't get past this door. And we don't expand any nodes from there. We can't stand on the door, even. So, aside from these two situations, we would just expand neighbors as normal. So, for neighbor in get neighbors, if neighbor in dist, so that means we've already put it in dist, that means we've already treated it as put it in the queue before, so skip this. Get neighbors. Get neighbors is specifically walkable neighbors, yeah. So then dist neighbor equals dist current plus 1 q dot append neighbor. Is it as simple as that? Nothing, no other checks needed? So we stop until we've hit keys in every possible path, or just like dead end or whatever. And then turn the mapping so we got all the keys and the distances. So we can test this. Let's test this just by getting the reachable keys from start. Okay, so we start with an empty set, so holding no keys. I missed something. Do you still have a breadth first search or Dijkstra? Well, breadth first search is what I'm using to find all the reachable keys from where I'm standing. And Dijkstra is sort of the outer layer, so that's using the knowledge of how far each key is from us. We treat those as nodes that we can go to. And in each step, we would get reachable keys again from when we're standing, which might be too much work, but we can try that to begin with. So I'm using both, basically. In each step of Dijkstra, I rerun breadth first search to find all the keys I can get to. pause. Return. So, oh yeah, of course. This is pause. I pause. J. Yay, we got nothing. Okay, it's broken. Oh! This check is redundant. We need to say if self.required key current is not none and okay, because none is not in the keys list, so this is always failing. All right, do that again. There we go. So we've got H at distance 10, E at distance 32. Okay, that looks very believable. I mean, we can test that on one of the easier examples. Just make sure it's actually correct. So I'll paste in... Okay, I like the look of this one. A, G, B, F, D, H, C, E. That sounds like a lot. Oh, no, that does look about right. Hang on, so A, 1, 2, 3. Definitely use the examples on this day. Actual input is a B, C, yeah. G, 3, B, 3, F, 3, D, 1, 2, 3, 4, 5. H5, C5, E5. Okay, it's quite symmetric, but yeah, clearly we can't get past B. So now we can change it. So we can say if we're holding key A, so now we're holding A. So that unlocks... Ah, no, because B is the next... Oh, damn, hang on. Yeah, there's an issue, yeah. Ah. No. No, that's not an issue. B would still be... Yeah, B would still be where we stop. That's correct. But... if we held key B... if we happen to be holding key B, okay, let's try this one. So this one I think will have an issue. If we're holding A and B, it's the same. Okay, but it's not what we want. If we're holding A and B, we do want J to be the next key, not B. So basically, we want to skip over any keys that we're already holding, because that's not a reachable key anymore under our semantic meaning of this method. J would be the next one. So we want to say if, so where we said if it's a key, and self dot get pause current not in held keys, then we would treat this as if it's just empty space. if we had it in held keys, then we would just treat it as if it's empty space. Let's try that now. Yes, so we don't get B or A, because we're holding A and B already. J is the next reachable one. Perfect. 1, 2, 3, 4, 5, 6, 7, 8. Okay, are there any other tricky twists? I don't think so. So if I held A, B, C, D, E, F, G, H, so we could just say set of A, B, C, D, E, F, G, H, K, N, J, O, L, M, I, P. That looks pretty good. Okay. So that's step 1. Next step is now to implement Dijkstra. We'll continue with this basic example here. So, get state, empty set. Okay. So Q equals priority queue. So we need dist equals a hash map. Initial state goes to 0. Q dot put. So we want to put the item. So the state and the priority, which will be, it'll be 0, but let's just be precise about how we're computing that. The dist to that initial state. Wait, what? Oh, you have to put it in as a tuple. Yeah, you don't give priority as a separate parameter. Okay, so put the dist as the first parameter. Of the tuple. Make sure this runs. Okay. So while not q dot empty. Okay. So Okay, so we want to... Man, this is harder to think of. Dijkstra is always a little bit harder to think about than BFS, but in principle, it's just... You're just substituting the priority in. So, okay, so we want... I don't think we care what the priority is right now. Actually, we kind of do. So distance current equals q.get. Now, if d happens to be bigger than what we're currently storing in dist. No, wait. Yeah. If, because the priority queue doesn't have an easy way to delete redundant stuff. If we found a faster route to something, we would just put that new thing in and the old thing would still be in there. So if D is bigger than current is a state, then the distance to this state. That means at some point we put this in with this priority, but then we later found a better route. I'm guessing that probably won't happen because of the tree-like nature of this, but if that did happen, we would actually just discard this. Lazy deletion. We only want the one where that is actually the fastest known distance to that location. Okay, so we have, and now we don't care about what D is. So current state, so we can unpack current pause, current keys equals current. We need to do a goal check. If we need to know how many keys there are. It's not up A to Z, is it? Well, no, it's not, because in these test examples it's not. So we need to actually make a count here. So keys, we store them here. So we actually want a goal. And goal can just be a number of keys. So grid.start length of grid.keys. If length of current keys wait where do we stop? We stop when we picked up the last key. So we've arrived at a key that we don't have, and our current, and so that makes our total plus 1 for the one that we're standing on is goal. That's when we stop. Count the keys from the input. When you have all of them, you're done. Yeah. So we're storing that basically as this parameter here. So if length of current keys plus 1 equals goal, because in every step of this we've actually moved to a new key, except for the initial state, I guess. But that's fine. I mean, we could be extremely accurate here. So we could say, if let's say, if grid dot is key current pos. So basically we've moved to a key which we don't have, because by definition that's what we did with this BFS. And length of current keys plus 1 is the goal, then we're done. What do we return? The distance. Return D. The distance. Or just say return dist current. Let's do that. No. When we put this in the queue, we'll have added this key in. No, we won't have. Will we? Hang on. I think, distance. Yeah, no. The moment we're standing here, it's as if this key doesn't exist on the map anymore. This is wrong. This will actually be in current keys. So we just have to say if length of current keys equals goal. The moment this comes out of the queue, it's as if we now have that key and it's no longer on the map. Yeah. So basically, the number of steps it took to get to this place where we're holding all keys. Okay, so that's the goal check. So ideally, we should never exhaust this queue. Unless something went wrong. So, with this goal check out of the way, we don't have all keys. So it should always be possible to find new reachable keys. Unless the doors are in soft lock places, so that should, we're assuming that wouldn't happen. So now we can run the BFS. So, reachable keys equals grid.get reachable keys from current pos current keys. So that'll get a map of keys. And it's taking us to all reachable keys that are not already held. So these are all guaranteed to be neighbors, new neighbors that make sense to go to. So for key running out of variable names, just say path distance in reachable keys dot items. So for No. Location. Or pause, whatever. Yeah, it's giving us the location of them. No, it's not. What is it doing? Keys equals... Distance. Wait, what do we want? Oh... We actually want both the location and the distance. We don't know... yeah, this needs to work out both of those things. So we should actually say keys equals current and distance to current. For key... Hello, Gun Voidwalker. No idea what's going on. I'm just happy to be a part of it. Do you do any coding in Python? And do you... Oh, thank you for the follow, by the way. Have you ever looked at Advent of Code before? This website that I'm using. Running out of variable names. I have so many warnings about having multiple variable names, yeah. Couple of thousand of hours of Python. So can I just do this? Just say pause path distance. Can I even do this? Can I unpack them this way? I can't remember. We'll try. So... So, we need to work out what the new state will be. So the new position, neighbor pause equals, well, that is just that. Neighbor the new set of keys. What are we calling it? Just keys. Let's call it held keys. Just be very clear here. If that works, that's a new Python thing to me. I don't even know. We'll find out. Neighbor held keys equals so it'll be current keys. We should say current held keys union just this one new key. So that will create a new set without modifying the current set. So neighbor state, we'll just say neighbor equals get state. So it'll be neighbor pause neighbor, and we can just do this. So that is the neighbor state. The neighbor distance equals dist to current plus path distance. So we now have a neighbor and a distance to said neighbor. We should do the check. So if it's already in dist. So if neighbor in dist and dist neighbor is actually less than what we found here, then this is redundant. We've already found a better path before. I mean, if it's less than or equal to, because if it's less than or equal to, that means we found this distance before. So right now we found a better distance to this neighbor than infinite if we never found a distance to this neighbor before. Oh man, this is getting hard to keep track of. So now we want to actually put it in the dist table. So dist neighbor equals neighbor distance, and then q dot put. So it's going to be so in Dijkstra you just put the full distance, don't you? So it's going to be neighbor distance neighbor. Yeah. Alright, that was a mouthful. There's many ways this could go wrong. Neighbor using the state. Okay. If we somehow get here, we want to say print, I don't know, error. Goal not reached. So we're returning the distance, the shortest distance to getting all keys. So ultimately it should just be whatever value this spits out. Okay. Run. String and set. Current held keys is a string? Ah, of course it is, because we wanted it to be hashable. So just say key string equals current. We need to make a set out of that. Like the best way, the cleanest way to do it really would be to create a custom class for a hashable class of keys, but we can just keep going back and forth with this. We can say this equals set of key string. Pos needs less than defined. And now, oh, 136. That's for this. Is that actually the answer? No. Yes, it is 136. Right, should we just test all the examples first? We'll just test the examples at the end. So there was this one. So this should be 132. 132. Now, it took a while for that big example, so I'm worried that the whole thing will actually just take forever. But, I mean, at least we've got a sort of correct answer for the examples. So this should be 80. This one should be 81. Okay. Oh, man. Now. God, man, this is huge. It's not gonna run, is it? We need something better. Try running it. I do want to see what kind of progress we're making, though. So can we say... can we print out... max keys equal 0. Let's say if hang on. Yeah, so if length current keys is greater than max keys, max keys equals that, print max keys. I want to see how many keys we get to. Also, how many keys are we expecting? Alright, start again. 26 keys, okay. 7, 8. Now it's slowing down. I mean, that's halfway through the keys. But yeah, running this shortest path algorithm every time, that's the step we need to cut out somehow. It's still climbing though. So now the question, we can use BFS to work out if this is a tree or not. That's an application of BFS. We just want to ignore this cycle at the start. Is this the actual input? Yes. I'm running it on the actual input, yeah. So we're trying to get to 26 keys. We're getting as far as 12. It's climbing, so might get there, but I feel like we need an all nodes shortest path algorithm here, so that we don't need to keep calling BFS. But yeah. We just need to ignore this bit here. I mean, I could just assume it's a tree because it looks like a tree, so we could just run it as if it was a tree. In which case, what I do is I use Floyd Warshall's. I mean, it's still climbing at a reasonable pace, so Floyd Warshall's all shortest path algorithm to find the shortest path between every pair of points. And not only is it shortest path, but it is the only path. There's only one path between every pair of points if it's a tree. I mean, apart from this middle section, as I said before. And you would have to qualify each of these paths, not only with the distance, but all the doors that are in the way, I suppose. Then, every time we're doing BFS, instead of doing BFS, we'll just call up our Floyd Warshall table, which we've pre-computed in like cubic time, so that's... It's still going to take a long time, isn't it? It's cubic in... Well, let me look this up again. Floyd Warshall algorithm. Yeah, it's cubic in the number of nodes. How many nodes do we have here? It's something like 80 times 80 over 2, because like, I don't know, like roughly half of these are walkable nodes, so it's going to be 80 times 80 over 2, which is 3,200, so 3,200 cubed. That's still quite a lot, isn't it? 3,200 to the 3. Yeah, that's too much. But it's a tree. So it actually shouldn't take that long. We can actually... We don't need to use Floyd Warshalls. There is actually... you root the tree, and then the path is right there in front of us. You go to the root of the tree, and then for part 1 I initially had 3 searches. You seem to have 2. I eventually rewrote it to just have 1. Still takes about 5 seconds, which seems long for a part 1. 3 searches. Interesting. Oh, we're up to 20. Oh, wow. We're actually going to finish. Okay. Because this... I think the key to this is using it as a tree, in which case the path from any node to any other node is completely known. Once you know the tree structure, you just find the... lowest common ancestor of both nodes, and you take the distance to that ancestor and then a distance from the ancestor to the other node. That's the algorithm. So once you know the tree, in constant time, basically you can find the path and the distance. But that means coding up a tree and everything. It looks like we'll actually finish, even though this is a crazy long time, but it's not completely unreasonable amount of time. But yeah, once you use... I'm guessing for part 2 we will actually have to go to a tree implementation. And we could just say the root is the union of these 9 squares in the middle. Sort of. Well... Not... Not quite. That's not quite correct. We can figure something out with that. But, oh, if it's the wrong answer, I'm going to be a bit disappointed, though, because this is working on all the test examples. I am printing the result correctly, aren't I? I hope so. We're returning the distance to current, which is number of steps until we're holding... Yeah, should be. But yeah, it's just like... Alright, there we go. 3, 2, 1, 6. Alright, I might not do part 1 this stream. Part 2 this stream. We'll just take a sneak peek at it. Correct. Took a while, but we got the correct answer. Let's read part 2 then. You arrive at the vault only to discover that there is not 1 vault, but 4, each with its own entrance. On your map, find the area in the middle that looks like this. Update your map to instead use the correct data. Like that. This change will split your map into 4 separate sections, each with its own entrance. Oh. This is interesting, because it's sort of... Splitting it this way makes it more of a tree than before. But now we've got 4 parallel robots. Okay, so because some of the keys are... It would take much too long to collect all the keys by yourself. Instead, you deploy 4 remote-controlled robots. Each starts at one of the entrances. Collect all of the keys in the fewest steps, but now each robot has its own position and can move independently. You can only remotely control a single robot at a time, so it's the sum of their steps. Okay. Interesting. Collecting a key instantly unlocks any corresponding doors, regardless of the vault in which the key or door is found. My first thought is that it doesn't seem much harder than what we've done right now. But... yeah, no, it is, isn't it? Because your positions of the robots... You got 4 different positions of the robots as your states. But assuming I move to the tree implementation, you've now got a rooted tree from 4 different roots. So that will cut out the whole inner BFS. Welcome back to Advent of Code 2019. Day 18. On to part 2. So, last time we had this map. With a bunch of keys and doors, and we had to find the shortest route in which we can pick up all the keys, noting that you can only get past a door if you're holding a certain key. Okay, that was the problem. And then part 2 was the same map, but we change. So this is the starting point. We change that to look like this, so that you've got 4 separate starting points. And yeah, and you got to basically do it again, but you've got 4 parallel robots. Not parallel. Well, they are. I don't know. They're independent of each other, but you kind of need to get a key for other. If you pick up, say, if one robot picks up key A, then the other robot is able to go through door A. So they all have the key essentially. So. Hello, DJ. So I'm thinking if you pick up a key to a door, then logically the very next step should be to go to that door, whether you go to that door or one of the other robots goes to the door. Because otherwise, why would you pick up the key? Oh, no, that's not true. The answer to why would you pick up the key is because it's nearby, and later on it won't be within reach. Okay, forget that line of reasoning. So I would think this is really same as before. Not breadth first search, Dijkstra. But it's trickier. Let's stop music as well. Because our state space is the 4 different locations the robots are in. And as coupled with the amount of keys we're holding across all 4 robots. So does that make it much harder than part 1? It kind of breaks up the map a bit, but it does also... I don't know. I mean, so one thing we need to... So before I said we would use something like Floyd-Warshall's algorithm to work out all the paths. That was wrong. Well, not quite. In a tree, you don't need to use Floyd-Warshall's algorithm. You just run breadth first search from every node, like from every key, to find the distance to every other key. That's quadratic time, isn't it? In the number of keys. No. number of keys times number of spaces. So yeah, that's kind of quadratic time in the number of spaces, but actually less than that. So we don't need to do shortest path algorithm. That's more for things with cycles or negative edges and stuff like that. It works in all cases. Here we've got a tree, so it's just far simpler. So we can work out, pre-compute the distance between every pair of keys and the set of doors that are along that route. So you can only go that route if you have all those doors, all those keys for those doors. Okay. So that's what we need to. So let's rewrite BFS, and I'm guessing once we do that, we run part 1 again. It should be much quicker because we just use those values. Let me grab a drink. So let's do that then. So we want to first rewrite BFS. Well, not BFS. BFS is, well, get reachable keys. Yeah, get reachable keys from a spot is going to there is a slight issue here, because if there are 2 keys along a route, we don't really want the further key to be a node that's reachable, because we... or do we? Because we might collect the intermediate key and then... Oh man, this is a bit confusing actually. Because what are we actually trying to do with this BFS? What is the end goal? We want this. Is this the same puzzle from a couple of days ago? Yes, part 2. I didn't try part 2 before, only part 1. I reckon it doesn't matter. I think we just find the distances between every pair of keys, regardless if the route includes another key. Because even if we take a suboptimal route where we walk over a key, we can pretend we just ignore it, just leave it on the floor. Now, you're not allowed to do that, but it's not harming us by pretending we're leaving it on the floor, because there'll always be a shorter route where we did stop at that key and pick it up, and we'll probably find that using the algorithm. So it doesn't matter if we allow ourselves to ignore keys. It doesn't make it worse. So yeah, this method is going to find... Let's make some notes here. Find distance and doors and accumulated doors in all key to key parts. Doors. Okay. Okay. So our state is going to be just like well, held keys doesn't matter now. Okay, take that out. Just finding all reachable keys from start, and for each key, should we say, for each key pair in the hash table, we have a pair. The result will be a pair with the door, the distance, and the doors. Something like that. So, and then no. The index of the table will be the one key, and as a result will be a triplet. Oh no, wait, no. Wait, how do we do this? Okay, the index of this table will be... Oh, no, we're starting at a specific location. So we actually just want a list of locations along with their distances and door paths. Is that it? Yeah, something like that. So we get list of key destinations. Okay, fine. Let's get started on this. So Q, use a DQ, let's start. So the state is not going to be just the location. But oh yeah, it could just be the location. But we'll need another map. Doors. Okay. That's... oh, it's not as... it's going to be an empty set. So that is a mapping of locations to how many doors you would have passed if you reached that location. What? No, not how many. The full set of all doors you will pass on the way to that location. So we start off with empty set, 0 distance, put it in the queue. Alright. So we fetch... so if we arrive at a key... and... so if it's a key... we don't need this anymore. Then... keys... so just say result is this. So we're going to do result dot append. So the result we want is the distance. So it'd be no. The actual key. So it'd be the letter. So that distance. The letter, the distance, and the set of doors. So, doors. And then... but we don't continue. Carry on, because we still need to expand more nodes from here. Ooh. Okay. If required key... oh yeah, we're not doing this. Okay. So for each neighbor, you get neighbor's current. If it's in dist, that means we've done it before, so skip it. So the dist of the new neighbor is +1, correct. If the new neighbor is a door. So if... What's the method we have here? Required key. If self.required key of instead of saying doors, let's say required keys. Because we don't care about the capital ones, we care about the lowercase ones. So required keys. So if self.required key of neighbor is not none, that means it's a door, then new then required keys of this neighbor is gonna be required keys of current union with this particular key. Else it will just be this alone. Number of the doors keys required for this path is the same as keys required for the previous node. And then q.append neighbor. Is that first one supposed to be key or keys? This variable here? This variable is a set of keys. And right above it, this one. This is a unique, this is one key or none. It's one or none. It's telling us what is the key that's required to enter this specific spot on the map. So it's either an empty spot, in which case it's none. It should return none, or it's just one letter. So the keys set will add in that one letter as a singleton. If it's not none, and if it is none, then we just copy the required keys set for the previous node into the new node. So this should just accumulate keys, and because it's a tree, there's a unique path between locations. So we never deal with multiple paths with different key sets to a goal. Hopefully. It looks like it's a tree. I'm trusting it to be a tree. Let me put that on the queue. Then we return result. So we search the whole map. So if we just run this for every key, we should just get a list of reachable keys. Alright, we'll try. And then this needs to be reworked. So just comment this out for now. So does this run? Okay, now we need to actually populate this. So we say key, or I don't know, path table equals that. Alright, so we want to try every key location as well as the starting location. So we want to say for start in, so it's going to be so it'll be grid dot start alright, this is grid.start will actually have to be a list because there can be multiple starts. So let's say it starts off in this empty list. Starts. Self.starts dot append that. Okay, so for each possible start, and initially that'll just be one thing. So it'll be grid.starts, that's a list on its own, plus all the keys, grid.keys, that should also be a list. Yeah, oh, it's a hash map. Because we're mapping... what are we mapping? We're mapping characters to positions. Alright, so we want... Basically, we want grid.keys.values to get the positions. Should be fine. We do grid.get reachable keys from this particular start. I'm going to try running that now, see what happens. Can only concatenate list, oh for goodness sake, list, cast it to a list. Okay, so it just ran BFS from every start location. Now we want to get destinations equals that, so that's going to be a list, or just say for. So it's going to be 3 things. It will be the position, the distance, and the set of keys you need. So for position, distance, required keys in that. Path table so this variable here maps what a right, let's say path table start is an empty list to begin with, and we just pile things into it. path table start dot append this triplet. Is that what we want? Position, the distance, and the required keys. Position, pos. We'll just say for triplet. Just put the triplet in as a tuple. Wait, what am I doing here? Just say path table start equals this. Yeah, that's it. It just goes. We just take the output of that and put it into the map. So is that fine so far? Okay. Try printing path table now. It's going to be a bit bulky. So position I40J40 maps to a list. So it's saying H so that get pause. What does get pause do? Oh, get doesn't get the position. We don't want that. We want literally just the vector current. Okay, so I4040 map. All the reachable keys are this one. So it's whatever is there. Wait, are we skipping? If self.isKey current, if we start from a key, we don't actually want to add it to this list. So if current not equal to start and okay. Oh, no. Like that. Yeah, we don't want to add the start to its own list. Okay. Try that. So, for example, 4040. Is that the start location? I think so. Would possible reachable places are this one at distance 10. No doors are required. And there are some 2969. It's distance 420 and has all these doors on the way. So some of these need a lot of doors. Okay, it looks about right. I mean, I could test an example to make sure these are actually correct, but the variance here looks roughly what I would expect, so... And this far away one needs all these doors. Okay. So now, we have this path table which is fixed. We never have to recompute it. So now if we run Dijkstra using this path table, we never have to compute any more intermediate distances. It's all stored here. So we want to run Dijkstra from a starting location to a goal. What's goal again? Number of keys. Okay. Let's rename that to goal num keys. Okay. And we want to give the path table as well. Given start, a number of keys we're aiming for, and we want to find the shortest route to get to that goal number of keys, which is all keys basically, and given a path table. All right. We don't need this anymore. X keys. So given a state, which is a position, and a set of held keys. Yeah, let's do that. So we start off with start set 0, blah blah blah. So this all stays the same. We're not doing this. If we get to the goal number of keys, we return the distance. Yep, sure. All right. Reachable keys. This is the bit where we're doing a massive amount of computation. So instead of doing this, take that out. So we're computing all the neighbors. We're going to want to go for each. So for it's going to be so basically neighbor, path, distance, required keys in path table for the key that we're sitting on, the location we're sitting on, which is current pos, neighbor, so neighbor state, so neighbor pos, okay, call it neighbor. Neighbor is a state. Neighbor is going to be get state of neighbor pos and union with key. Why did I do it like this? Oh, I see. Yeah, okay. So the key will actually be grid dot get pause neighbor pause. That gets the key. So current held keys, we add one new key to our current held keys, our key ring, essentially. Neighbor distance equals that path distance, which we pre-computed, added. So for these required keys, what are we doing about that? We're saying we're only counting this neighbor if required keys is fully contained within the set of keys we're holding. But what if you were to get a key along that path that you would use? Well, we're not really counting that, are we? So we'll say that path is invalid and we'd actually have to go to the intermediate key first. Makes sense. All right. So we say if what is this the method we use here? Python set containment. We want to say if is a subset of another one. P dot is subset of S. So we want to say if required keys dot is, what is the method? Is subset of current held keys. So if these keys will let me cover all those doors, or if it's not a subset, then we can't pass those doors, so we skip this neighbor. So only the ones which we haven't seen before will end up added to the queue. Alright, will that work? Don't print this. So we want just that. Length grids, keys. So the goal is that many keys. We need to provide the path table. Alright, try it now. How long is it going to take? Quicker than before. Much quicker than before. Still longer than I was expecting. I suppose. Seems about right, maybe. And we can print this just to see the progress being made. Yeah, it slows down a bit, but way faster than what we had before. 3216, is that the correct answer? 3216. Correct for part 1. Alright. So we've redone part 1 in a much more efficient way. A bit more confusing to understand now, but that's sped it up from minutes to seconds. Alright, good. Now, part 2. So do we want to make Dijkstra a general case, or we'll make a duplicate of Dijkstra and modify it slightly? Let's do the latter. So we're gonna say okay. Part 1. Just put part 1 here. So now part 2. Will be... Alright, we no longer need to print that. Or... this. Alright, and then... defining a new Dijkstra. Subtly different. Dijkstra 2. Given 4 starting locations. So it's going to be a tuple of specifically 4 starting locations. Go num keys is the same. Path table is the same. Now, path table will actually be simpler this time, because we've broken up the map, so the reachable keys from each key is is less. The number of... Yeah, because there'll be fewer keys reachable each time because we can't cross the middle. We can put those on. Alright, so we're given 4 starts. Or a tuple of starts, I guess. Just say 4 because we know it's 4. So you got get state of, let's just call it pos tuple so we don't forget it's a tuple. It's that initial state equals get state of starts set. Initial state distance is 0. Okay, this is going to be as normal. Tuple. String equals current held keys equals that. If length current held keys equals goal num keys, return distance. Okay, that's as before. Oh yeah, we could do that as well. All right, now this bit changes. So this time we're going for each pause in this 4-length tuple. We're trying to find the path from that particular key position. So how are we doing this? We're going to say for I in range, or say for, let's say, pause tuple index pause in enumerate current pause tuple. So we go 0, 1, 2, 3. And then for that whole thing, so we've chosen one index to fix, and we're saying for this index, we're going to go from this particular pause to the next key available. So it's going to be for neighbor pause, path distance required keys in path table, it's gonna be that, I guess. And then this will stay the same. Now this is gonna be different. We're gonna say, so neighbor. Yeah, it's not quite going to be that. So yeah, if we don't have the keys, we don't take this path. Otherwise, we do. All right, so we're saying this particular position in the tuple is going to change to whatever we get here. But everything else will stay the same. So it's going to be like new pause tuple equals list of current pause tuples. So turn it into a list. Change this particular index to the new position. And then tuple it up again. Just a long-winded way of doing that. All right. And then once we have that, the neighbor, the overall neighbor is going to be get state using this tuple. Those keys. And the key that's picked up at that specific one spot. Neighbor distance equals distance of current. What was current? Yeah, current is that. Why doesn't it like this? We've done dist current here, but it doesn't like us doing dist current here. What exactly is current again? What's this? Should be fine. Or it doesn't like this statement here? I don't know. So the new distance will be previous distance plus the path distance, which we get from here. If neighbor is in dist, and we found shorter path before, continue. Update that, and then put that in there. Should work then. So we're moving all the 4 robots turn by turn. So in each step, in each phase, we take one robot of the 4, send him to one of the keys he can reach, add up the total distance he took to get there, but also make sure that all the doors along that path we currently have the keys for. And then that's a new state, right? And then just do that. So now that is the new Dijkstra. We have to change the modify the grid. We're gonna have to say we're gonna have to make the grid mutable. So say grid equals, it's gonna be list row or row in grid dot grid. Convert everything to a list. So just check that looks correct. We don't need to do part 1 anymore, just turn that off. So yeah, now it's mutable. Okay. So center equals grid.starts 0. Print center. Because that should be... Okay, 40-40. So now we're going to have to change each of these things according to what they said. So How does it work? So grid dot grid. So the row will be, I don't know, just hang on. Center is a pause. All right, so center dot I, center dot J equals, but oh, hang on. So this one is going to be, okay, start from the row above. So it's going to be row -1, and then start from the leftmost corner. So that'll be J-1. That's going to become an ampersand. And then the next one along so it'll be I-1J will become a hash. And then I-1J plus 1 will become ampersand. And then the middle row, it'll be hash, hash, hash. So it'll be I, and then those J's will be hash, hash. And then the final one will be +1, +1, +1, and it's going to be ampersand, hash, ampersand, like that. Okay. And now should we just make it immutable again? Just nice safety thing. So now grid.grid equals dot join row for row in grid.grid. And now for row in grid.grid print row. Alright, see what this looks like now. So where's the center? There. Alright. Looks alright, I guess. Okay. We don't need that. So now, don't need that. Grid.starts is going to change. So grid.starts equals, so it's now going to be so be center plus, so it'll be -1, -1. And then just, it's going to be the 4 corners. So it'll be center plus, pause, 1, 1. Center plus, so it'll be 1, -1. Center plus, let's do them in order from left to right. So that'll be -1, 1, -1, -1, -1, 1, 1, -1, 1, 1. Okay. So now the grid is just looking at a new grid. So we can run get reachable keys again, and it should just use the same logic. So do this. Path table is empty. The start in grid.starts plus all the keys. So it's starting from each of the starts as well. Yeah, we add the path table. Make sure that runs. Okay. And now it's the big step. We do this basically. Print Dijkstra2 for it starts. In that path table. Unhashable type list. Initial state. So that should be a tuple. Did we wrap it up as a tuple again? Oh, yeah, of course. Part 2 should be tuple of grid.starts. Not a list. Alright, go. Oh, it's going quite quickly. Okay, it'll take longer than before, but that with that momentum, I think we'll actually get there. The fact that it's taking longer is actually promising, because that means it's doing something different to before. We don't want it just running the same logic as before, because then that'll be wrong. Yeah, it looks like we'll get it. Will it be correct? I don't know. Is that logic correct? Each node... So state space... Seems correct in my head. This will no longer work on part 1 though. We can adjust Dijkstra1. We can reuse Dijkstra2. We just have to pass this starts as a tuple. We'll see if it works. Wow. There we go. 1538. Now, does this sound right? It's roughly half as many as it was for part 1. Because we've got 4 robots and the space is separated. That sounds right, because then across the robots they're working in conjunction with each other. It should theoretically be quicker, right? To collect all keys. Because you're collecting keys within the 4 segments. Yeah, it should by definition be quicker. You never have to have your robot go across the middle to get somewhere, because he can just send the robot that's already down there. So... yeah. But, is it the correct number? Whew. Correct. Wow. I anticipated running into more trouble here. I felt like the branching complexity might be a bit higher, but it's not much higher. It did take longer to run, so clearly it is higher. But it's balanced by the fact that you've now isolated 4 regions of the map. And you've compartmentalized it. With exception, because you do still need to coordinate. Like, you know, one robot picks up one key that another robot needs. So it's not, you're not solving 4 separate problems, each of a quarter of the size. No, you're still solving that one big problem and coordinating the 4 robots together. But branching, there's just not as many branches, because there's either you send one robot to these keys, or you send another robot to these keys, and so on. Before, it was you send this one robot to any of the keys. Every step. So it's just an interesting change. And if we look at the code, I could make this work on part 1 as well. So if we just say this is the new Dijkstra, all right. So we use it, calling that Dijkstra. Get rid of the old Dijkstra. Alright, just move this. To here. Alright, so this is part 1. So starts, yes, that still makes sense. So when we call Dijkstra here, it just says one item, so we want tuple, just like we've done below, convert that to tuple. This is a 1 length tuple, which is fine, you can do that. And then the algorithm should just work. And give us the same answers before. So this is part 1 now. And then it will move on to part 2. It's a bit quicker. 3216. That is correct. Okay. So this actually is the new and improved general case Dijkstra for an arbitrary number of robots all working in parallel. And starting at different starting positions. In this case, I mean, in part 1, there's just one. And that's cool. That was a cool problem. It was not actually as hard as I thought it would be. I thought we'd have to be a bit more clever than just running Dijkstra. But Dijkstra is not exactly an easy algorithm. Like, you know, I've done it so many times, and no matter how many times I do it, it's always, you always have to think hard when you're writing it. It never gets easier. Because you always have to customize some part of Dijkstra. So you can't just copy and paste the pseudocode. There's always some twist. There's always something in the, I don't know, like the state space or the distance function, the get neighbors method. Something is always different and different from the norm. You could be, I don't know, like on a hexagonal map, or you could have a scenario where your neighbors, you're only allowed to move in one direction or turn, because we had that this year, didn't we? So your neighbors aren't just, you know, forward, left, right, up, down. Your neighbors are either you move forward or you turn on the spot, and now your new neighbor is still staying in the same place, but you're now facing a different direction. That is one step. So that is a distance. So that's like, that is your neighbor space. Sometimes you have weird measures of distances. Sometimes it's a cyclic map. Sometimes it's acyclic, which was the case here, with exception. There was one cycle at the start, but if you pretend that cycle doesn't exist, because it doesn't matter, that particular cycle didn't matter. Any other cycle probably would, because it would mean there are routes to keys without crossing doors. That would be a whole different problem. I guess that would be NP hard, because that is actually essentially the traveling salesman problem. but in a way it's harder than the traveling salesman problem. Because if you took away all the doors, and it was just a question of getting all the keys, that is still the traveling salesman problem. That is still a hard problem. Shortest path to cover all keys. That's MP hard. Put the doors in, and then suddenly you have something that's even harder. Is it still MP complete? Yes. Because you just give the route and then you have your certificate. So it's still an MP complete problem. But we're on a tree, so that's the key here. Alright, and I quite liked using DQ. I guess I should use DQ more often because the syntax is more like a list, and often I interchange using a list or a queue depending on whether it's DFS or BFS. I mean, if right now I were to do this, now it's doing DFS. Oh, okay. You would have to do q.pop, not pop left. But oh, if you do okay, so if we were to forget using DQ, double-ended Q, and use a list, which is the slow way, because now you have to realign the list in memory every time. Let's see how much slower it is out of interest. Pop. So we do pop 0, popping from the front of the list. So now we're not even using a... It's the same speed. Because Python's pretty optimized for small lists. So you're only moving like 20 things in memory, so... No, you're not moving 20 things in memory, you're moving... I guess the depth is... Oh no, this one is... Yeah, this one you only have 20 things in memory. Yeah. So it's not that much slower, but it's good practice to use a queue, because it is actually better. I mean, especially if you're doing pathfinding in like a video game or something. At some point, you might be okay with lists, but you would be able to get some better pathfinding, especially if you've got lots of enemies with long distances and stuff, and obstacles for them to get around. Q would probably be better. But you'd be using A star or something, so you'd be using a priority queue. Alright, that was pretty nice problem. Not as hard as I thought it'd be. Take a peek at the stats and get a preview of the next day. So it's day 18. So people solved it in... This is both stars. 2 hours. Wow. Really? $45 minutes for 17. For day 18, the one I did, it took them 2 hours. For part 1, up to 50 minutes. That surprises me. Because I wrote Dijkstra and BFS from scratch. But, I mean, I could just have copied in the template that I've written before and just change the, I don't know, the get neighbors and the states or whatever as needed, it shouldn't take that long. Alright, how long did I take to do that whole thing? This session took me an hour with a bit of waffle. What did the previous session take me? I've got the saved video somewhere here. 18 part 1. 2 hours. So together 3 hours. It took me 3 hours, but that's with a lot of talking and being pretty slow and writing Dijkstra and BFS from scratch instead of, like, people who do this competitively, they'll just have a library stored somewhere where they've done this before, so it's just paste in BFS. Why did it take them 2 hours? I don't understand. Like, it took me... I didn't think I was going particularly fast. It took me 3 hours, and I'm pretty sure if I could knock off an hour if I was doing this, you know, not streaming it. Got my templates of BFS and Dijkstra ready and everything. I would be in the top 100 for sure. But why? Because I didn't think... I'm not exactly competitive at these. I don't know. Maybe that year not many people were competing, or just... I don't know. Strange. Because other years, you know, they've done it really quickly, and I don't think I would beat them. And part 2 was not actually that much harder. It just changed from a 1 start to a 4 start 2 pull. I don't know. I think I would have... This is one particular problem I guess I would have been in the top 100 for then. Alright. It looks like 19 might be a bit easier. And then the rest are all kind of similar in difficulty, but varying numbers of... Well, look, these numbers are very different, but the star graphic, I guess it's all squashed up, so it doesn't... you can't... They're trying to align it with these big ones. So these big ones make the result, have the result of making all these ones all have the same number of stars, when in reality you've got 2842 here and you've got 164 here. That's a big difference in ratios. That's like 10 times, more than 10 times more. But these graphics are the same, but I guess that's just, you can't do much about that. Okay. Oh, and the leaderboard. Catching up. I'm now equal to Pararonia. Pararonia didn't do 18, it seems. Okay, and Captain Coda. I don't think Captain Coda is interested in doing these previous years. He's very busy with other stuff. All right. Cool. That's 18. So 19 might be a bit easier. I might do it tomorrow. So yeah, nothing else to say. See you next time. At this rate, we might actually get all archived years done before Christmas. Man, that'd be crazy. Alright, bye-bye.